Hello, I'm Martin Heckel, and today I'm presenting the paper Reverse Engineering Bank Addressing Functions on AMD CPUs, which I've written together with Florian Adamsky. We are both working at the Institute for Information Systems at Hofstra University, and I'm also a PhD student at TU Graz. I'll start with a brief introduction. Basically, our system's DRAM consists of multiple channels. Typical desktop systems have two channels. One channel can hold one or multiple DIMMs. And one DIMM contains integrated circuits that are organized in ranks. For example, one rank could be on the front side and one on the back side of the DIMM. These ranks consist of integrated circuits which contains the actually DRAM banks. However, there are systems where one bank spans multiple integrated circuits or where one integrated circuit contains multiple DRAM banks. Within such a bank, there is the DRAM array, there are amplifiers, and there's the row buffer. One row within the DRAM array has typically a size of 8 kilobyte. Let's take a short look on DRAM bank addressing functions. Basically, the physical address space is distributed over all DRAM banks. The DRAM addressing functions are implemented in the memory controller and determine the bank a physical address is stored on. AMD had published these addressing functions in the BIOS and Kernel Developer Guide until Microarchitecture 17H. They stopped at Microarchitecture 17H. Intel did not publish these functions at all, so basically research was focused on Intel until now. I'll explain how this address function works on a short example. So let's assume we have four address functions, f1 to f4, and we would have the physical address 0, which is shown as A with all zeros in binary. Then we could calculate a bit of the address function by applying a bitwise AND to the function and the address A and performing an XOR over the result. So for the first function, the result would be all zeros, and an XOR over all zeros would be 0 in the end. We repeat this for the other address functions, and as you can see, it's always 0 as a result. Now we just take the result bits, put them all together. It would be binary 0, 0, 0, 0, which would be 0 in the end. We repeat this with the physical address 1, 0, 0, 0, and again, for all address functions, the result would be 0, so it would be 0, 0, 0, 0 in binary, would be 0 in decimal, so physical address 1, 0, 0, 0 hexadecimal would map to bank 0 as well. If we repeat this for the physical address 2, 0, 0, 0, then we would have 1, 1 when we put the bitwise AND with the first address function, so the address bit would be a 1. For all other functions, it's 0 again. So now the result would be binary 1, 0, 0, 0, which would be equal to 8 in decimal. So the address 2, 0, 0, 0 hexadecimal would be stored on bank 8. Now I'll take a little bit more details into the AMD reverse engineering, address reverse engineering on AMD CPUs. The overall process is shown in this picture, and we'll take a look in each step. The first one is to determine the threshold. Basically, how long does a row hit take versus a row conflict. Therefore, we allocate a 2 MB transparent huge page and access the first and the nth address 200 times alternatingly, thereby n is a multiple of 4096. Afterwards, we measure the access time. Then we generate a histogram of the access times and search for a gap between row hits and row conflicts. We use the middle of this gap as a threshold. In the next step, we determine the number of banks. This will be explained with a little example. So let's assume we've already found 5 groups of addresses which we declare to be banks. And we've measured a threshold of 550 before. Now we want to group another address 1 to F000. We compare the address with the first address of group 0 200 times and measure the access time. We repeat this for the second address in group 0 and the third address in group 0. Then we take the median access time, which would be, for example, 500. We limit the number of addresses from each group to compare with to 9. So basically, if a group has more than 9 addresses, we randomly select 9 addresses and compare with them. Then in the next step, we repeat this for group 1, compare with the first address and the second address, measure a median access time. We compare this for the addresses in group 2, get a median access time, and we repeat this for group 3 and group 4. As you can see right now, the access time on group 1 and group 4 are both bigger than the threshold. So we could assume that both had row hits, which is impossible since there can be only one DRAM bank. It showed that this can happen due to noise and that it is a good approach to just take the group with the biggest access time, which would be group 1 in this case, so we add the address to group 1. When the access times are smaller than the thresholds for all groups, then we would just create a new group and add the address to a new group. This is also the case in the beginning when there are no existing groups yet. Afterwards, we regroup the addresses because there can be multiple pages in the same DRAM row, which results in a row hit even if they are on the same bank. So the groups generated before are removed one after another, and each address of the removed group is grouped again, using all other groups. This removes groups that were created due to row hits on the same bank in the step before, since there were fewer addresses before and thereby the possibility of having row hits in the same bank was higher. The next step is to determine the block size. Basically, one row in the DRAM array has a size of 8 kilobyte. So we could assume that there are blocks of continuous physical addresses which have a size of 8 kilobyte. If that would be the case, then we would only have to measure the first address of the block, since we would know that every other address of the block is on the same DRAM bank, so we wouldn't have to measure multiple times, which significantly increases the speed. However, there could also be a case where the block size is only 4 kilobyte, so we would have to measure 2 times. There could also be block size of 2 kilobyte and we would have to measure 4 times. Or there could be block size of 1 kilobyte and we would have to measure 8 times, and so on. Basically, the biggest possible block size would be 8 kilobytes, since that's the size of a row. And the smallest possible block size would be 64 bytes, since that is the size of a cache line. Now the question is, how can we determine this block size? And the approach is pretty simple. In the beginning, we assume a block size to be 8K. Then we measure the first address. Afterwards, we count the number of continuous blocks, which would be 1, because block 1 right now would be on another DRAM bank. So we know that there is exactly one continuous block on this bank. And since that is the case, the block size is either 8 kilobyte or smaller. We don't know this because we've not split this block yet. In order to resolve this problem, we have to split the block. We now assume a block size of 4 kilobyte and measure 2 times. As you can see, we have found block 0 and block 8. So block 1, block 2, block 3, block 4, block 5, block 6 and block 7 are on other DRAM banks. Therefore, the block size is 4 kilobyte or smaller. We divide it again into 2 kilobyte blocks. Again, the blocks are not following each other, so now we know that the block size is either 2 kilobyte or smaller. We repeat this again, split them up into 1 kilobyte blocks, and now we see that block 0 is followed by block 1, block 4 by block 5, block 8 by block 9, and block 2 by block 3. So we know that always 2 of these blocks are following each other. If this is the case for all blocks, then we can merge block 0 and block 1, block 4 and block 5, block 8 and block 9, and block 2 and block 3, and thereby we know that the block size in this example would be 2 kilobyte. The next step is to add additional addresses to the group. So a number of transparent huge pages is allocated in the beginning. Afterwards, the addresses of the transparent huge pages are added to the groups based on the block size determined before. The last step is to derive the address functions. We use a brute force approach, so basically for each possible addressing function there are some requirements that have to be met in order to add the function as a valid one. The first requirement is that the function yields the same result for all addresses within the same group. The next requirement is that it has a 1 as result for 50% of the group, and thereby 0 for the other 50% of the groups. And the final requirement is that all bits of the address function have to be relevant. There should not be an address function with fewer bits that yields the same result. So basically, if we toggle the bits to 0, then the result has to be different. Afterwards, we simplify the address function by removing linear combinations. We add some sanity checks. So the first one is that that the number of banks has to be a power of 2. So this approach does only work with linear addressing functions. The second one is that the number of addressing functions should be a logarithm to the base of 2 over the number of banks. And the third requirement is that the addressing function should be orthogonal, so basically divide all other addressing function results exactly in half. Let's skip to the conclusion. Firstly, this approach yields good result on the tested Intel and AMD CPUs. We tested this on an AMD Ryzen 9 5950X, a Ryzen 9 3900X, a Core i9 10900K and a Core i7 4800MQ. Also, the results are more constant than the ones of the Drummer proof of concept. However, this is at the cost of our proof of concept being slower at detecting the address functions. And finally, our tool is open source, so feel free to try it at the link provided in the slides. That's about it. Thanks for listening to the presentation, and now we have a little bit time for questions and discussion.